Thank you very much. So thanks Alberto, first of all, for inviting me here to give this talk. Thanks to all of you for being here. And then officially an apology for giving this talk in English. As I told you, I'm used to speaking English in a work environment and to talk about philosophy in English, so I feel more comfortable in doing the same here with you. So the talk that I will give today is one of the products of a project that I developed at the LSE until more or less the end of last year, so 2017, which was on scientific models, fiction and imagination. And this talk is basically the last result of that project. I've been working on a paper on this for some time, and this is a kind of outline of a theory of models as fiction that I have been developing during that time. Okay, so Alberto told me that you've read already some of the literature on the relation between models and fiction, so I'm sure that some of the things that I will mention today will not be new to you. But of course, if you have any questions, clarification questions that you want to pose to me while I talk, I think that would be okay, right, to do it during the talk. Otherwise, we can talk about everything at the end of the talk itself, of the presentation. Okay, so this is a problem that I want to address in this presentation. The problem concerns the representational function of scientific models. And the question is, how do scientific models represent in a way that enables knowledge of reality? As you may know, scientific models are constructed as tools for investigating, studying real-world phenomena that are too complex to be studied directly, right, like we would do in an experiment, for example, or through observation. And so what we have in this case usually is an idealized description of what we may call an imaginary system or an idealized system, a model system, that is used as a surrogate for the real system, the target system, that is the part or aspect of the world that we want to study. The relation between these surrogate systems, the object of study, the tool of investigation for finding out, learning about features or properties of reality, that relation is usually understood, construed as a relation of representation. But it is not just representation, it is a representation that enables knowledge of reality. So it is sometimes called an epistemic representation. More specifically, because we are in the context of science, we call it a scientific representation. Epistemic representations can be of many different types. This one is a scientific epistemic representation. Now, let me narrow down the problem, the question. So it is common among scientists and philosophers of science to distinguish between two main types of models. One type is what we may call a material model. A material model is a model, is a concrete or ordinary physical system that exists in reality. It is something that we can physically construct. We can touch it, we can observe it, we can investigate it, we can manipulate it. And by studying these concrete objects, we can learn things about real-world phenomena. So some examples, some famous examples are, for instance, the Watson and Crick's Bose-Stick's model of the DNA, which is currently exposed at the Science Museum in London. It is something that you can go and see there in the museum. Kendrick's Plasticine model of Myoglobin. This is a model made of Plasticine, right, that has been constructed to study the structure of myoglobin. The San Francisco Bay model, this is a scale model of the San Francisco Bay that has been created by the US Army to study a certain possible way of reshaping the San Francisco Bay and seeing what consequences there would be for the environment by doing that. Before constructing anything real, in the real San Francisco Bay, they constructed this small-scale model. Now, on the other side, we have what we call theoretical models. And theoretical models are mathematical models that specify a non-existent system that we want to study for the purpose of learning about reality. Because the model system in this case is non-existent, some philosophers have called these models also fictional. So if you read the Stanford Encyclopedia entry on models in science, you will see that Roman Frick and Stefan Hartmann call these models also fictional because of that reason. Among these classical examples, the first one that would come to mind is Newton's model of the solar system. In that case, you have a number of equations and theoretical principles, and they are the ones that specify the model system, the solar system that is the idealized, if you want to say, so the idealized version of the real solar system. Goldbetter's model of circadian rhythm, models in chronobiology, computational models in the social sciences, and of course the Lotka-Volterra model of predator-prey interactions. So now that we have this map, let me tell you that my question will basically focus on theoretical models because they raise the biggest concerns with respect to the problem of how to understand the representational function of models. You will see why in a second. So the key idea when trying to address that question, how do theoretical or fictional models represent reality in a way that enables knowledge of reality? The key analogy that I want to exploit, to build on here, is with fiction. The analogy is not new. In fact, originally it was presented by a neo-Kantian philosopher, Hans Weihinger, more than 100 years ago. More recently, in the 70s, in the 80s, this analogy has reappeared in much literature on models. However, only recently, in the last 12 years, let's say, since the publication of Peter Gottfried-Smith's paper on models as fictions, we have a strong, robust analogy between scientific models and the fictions of literature and the art. In the original version of that analogy, the analogy is with fictional characters. So we think about model systems. We characterize them as imaginary systems, therefore fictional systems, and it is natural to see them as the fictional characters of a novel, for example. So entities that would be concrete if real, that are predicated or attributed certain properties that only concrete objects would have. However, these are entities that do not exist. My preferred analogy is a different one. It is not necessarily one that excludes the previous one, but it specifies it in different terms. So I think that models are akin to literary works of fiction. While the model systems may be characterized through the analogy with fictional characters, I will try to reconceptualize the notion of a model and to think about it as a kind of story rather than as a fictional character. That's my idea. And the best account of fiction, the one that has been also used by others in this context to try and offer a more robust theory of models as fiction, is the Waltonian theory of fiction as make-believe. So the motivation for these accounts is the following. Sometimes it is implicit, sometimes it is explicitly made, but some of those who have worked on this particular project, and it is naturalism. So naturalism is a theoretical requirement that any theory of models should satisfy to be an appropriate theory, an explanatory theory of models. And naturalism says that any theory of models should be able to explain the modeling practice of scientists, so the way in which scientists think and talk about models, what they do, right? When we think about the model in practice, we have a characterization given by Martin Thompson-Jones, which is very useful, and it is in terms of these three claims. The first one is that scientists present model descriptions that specify model systems as the object of study. Model descriptions are things like the Newtonian equations, for example, of the solar system, linguistic assumptions, graphs, different symbols that we can use to describe these idealized imaginary systems that would be the object of study. The second claim is that model descriptions involve the attribution of properties that only concrete objects could have, yet there are no objects instantiating those properties. And finally, scientists are usually aware of this. So it's not that they are confused, that they don't know what they are talking about when they create these models. They know very well that the objects they are describing within the practice are idealized versions, simplified versions, abstract versions of real-world phenomena. And so the face value practice is a claim about the way in which scientists think and talk. And in particular, I would say it is a claim about scientific cognition, right? One about how they think about these objects, what they do when they learn about these objects, how they describe them, how they work with them, etc. Okay, now the outline very quickly, what we will do. First, I will describe to you two main adequacy conditions that any model as a representation should satisfy to be a scientific representation, one that can enable knowledge of reality. And that is based on the current literature on models. It is not something that I make up, but I will identify some problems that haven't been clearly specified in that literature. So we will investigate a little bit those two adequacy conditions. Then I will very quickly give you just a couple of slides on models as make-believe. Just a couple, because I assume that most of you are already familiar with the Waltonian approach. I don't think that we have to go into too many of those details, but I will, of course, give you one slide on that, where we will understand how that works in models. We will also briefly discuss two main standard views on models as fictions, and that will be aimed at explaining what the current problems with these views are with respect to the adequacy conditions that I will talk about in a moment. And then I will describe at the end my fiction view of models that I call the new fiction view of models, which is a type of amendment, but also improvement on those theories. Okay, so the adequacy conditions. Here is one example that I will use through this talk, and it is one that I use because it is very simple and paradigmatic. This is the Lotka-Volterra model of predator-prey interaction, which was independently developed by Alfred Lotka and Vito Volterra, the Italian mathematician, more or less at the beginning of the past century. And this is the first model of population dynamic, in particular a model of predator-prey interaction. The model is usually identified with the two differential equations that you see on the your left hand side of the slide. And these equations per se, they are just mathematical objects. They are not models of anything. To become a model of anything, and in particular a model of population dynamic, they have to be interpreted in a certain way. So the variables and the coefficients in the equation have to be assigned a certain interpretation. In particular, if you look at the first equation, the variables x and y, they stand in for the size of the prey and predator population, respectively. T stands in for time, of course. The coefficients a and b. A stands in for the growth rate of the prey population, and B stands in for the rate at which the prey population is eaten by the predator population. So the first equation is basically about the cycles of growth and decrease in the size of the prey population in interaction with the predator population. The second equation, Y stands in for predator. I told you C and D. C is the rate at which prey decreases, so the mortality rate of predator decreases. And the second one is about, D is about the rate at which predators eat prey. So through this interpretation of the equations, you get a model of the interaction between prey and predator populations. Now, what predator and prey populations? That's the question. To enable mathematization, this mathematical treatment, we need to make a few assumptions about the phenomenon of interest. And these are usually idealizing assumptions that help us to isolate the features of the phenomenon that we want to study. In this case, we say that prey have limitless supplies of food. So we don't get the problem of the contingency, right, of what the environment may provide to the prey. We just focus on the population size. That's all that matters for the model. The second assumption is that predators have infinite appetite, and the third one is that the environment never changes. Okay? So through these three idealizing assumptions, we isolate that feature that is the one we are interested in, which is the population size of these different groups. We can develop the model by assigning different values to the different variables. And by doing that, we get an outcome, a model outcome. We derive, we infer that the interaction through time of these two populations will be cyclical. So if the size of the prey population grows, predators will have more food. So their size will grow. If their size grows, the prey population will diminish, right? Because there will be more predators eating more prey. So we will see a decrease in the size of the prey population with less prey, less food for predators, and therefore a decrease in their size, increasing the prey population, because now there aren't enough predators to eat all of them. And the cycle starts all over again. So this is what the graph is graphically, right, pictorially representing to us. So now we've learned about the populations of the model. These are, we say, imaginary populations, because there are no real-world populations that have infinite supplies of food, that have infinite appetite, that live in an environment that never changes. All of these conditions are idealizing conditions that are enabled by our use of imagination as a cognitive ability that we have to divert from reality, from the way in which reality really is, and create these alternative realities, if you want to call them that way. So these imaginary systems. Now, that's still one step away from learning about real-world populations. The model can be used to learn about the interaction, the dynamic interaction between real-world populations, in this case, for example, foxes and rabbits. So we can use that to make some predictions about how these populations will interact. And that is done by exporting, converting what we have learned about the imaginary populations of the model onto reality. So that's the further next step, the final step that we need to make. Now, how can a theory of models as scientific representations explain systematically what I just told to you? How can we better understand this practice? And usually we have the recognition that there are at least two main types of conditions, adequacy conditions, for a model to be a scientific representation. The first one is what I call the aboutness condition, and it is the condition according to which an object is a representation of something else only in virtue of a certain type of relation with that something else, so an aboutness relation, something that needs to be clarified, but this is the idea of representation of, right? So if you want to understand this idea in another context, think about pictorial representation. The same problem appears there. You see a painting of Mona Lisa, and when you see that, you immediately see a representation of a woman. So you see a woman, but the painting itself is just a flat canvas covered in paint. So to understand how that can be a representation of something else, you need to understand what relation there is between the painting and what it represents, the object that it represents. Now, usually, a standard solution in the context of modeling is that of appealing to Nelson Goodman's notion of denotation, and I will not challenge that. I think that is a notion that needs to be developed. It is not very well understood, but that is not something that I will do today. So I will just agree with the standard solution and recognize that denotation is the type of relation that is at work to explain the aboutness condition. There is, however, a more important problem, one that is even prior to that of the relation problem, that still concerns the aboutness condition, and that is particularly problematic in the debate on models as representation. The problem is what I call the identification problem, and it is the following. Denotation is a dyadic relation between objects, a symbol, a denoting symbol, and an object, the denoted object. Since it is a relation, it necessarily involves at least two objects. It's dyadic, so it will be two objects, but two objects that have to exist to stand in that relation. Now, philosophers of models are still largely disagreeing about the nature of models, what they are. Even understanding the meaning of the term model sometimes can be controversial. Some philosophers understand them as model systems, understood as abstract objects, for example. Others understand them as structures, something different from model systems, structures like mathematical structures. Others have different ideas, perhaps structures plus interpretation, construal. There are many different options on the market. This problem is even more challenging and difficult to solve for the upholder of the fiction view, because the upholder of the fiction view of models claims, at least in the standard version, that models are model systems, and that model systems are akin to fictional characters. And there you go into the entire controversy about the metaphysics and the ontology of fictional characters. So our question is, what objects are models and how do we identify them? And there is no clear solution to this problem, not yet. Now, the last condition, the second, is the epistemic condition. And this condition is the one that makes models epistemic representations. Not just a representation of something, but a representation that enables knowledge of that something, that enables us to learn something about the object that is represented. How do models do that? There is a standard solution here, again, like in the previous case. And this is the idea that learning with models involves two steps. The first one is that we construct this surrogate system that we study to elicit its own secrets, to learn about its own properties and features. And then after we have learned about the model system, we go through a second step. We convert what we have learned about the model system into knowledge of reality. That's the second step that we saw with the Lotka-Volterra model. First, we get the model outcome, the imaginary populations, interact in a cyclical way. Then we transfer that onto reality, and we use that to make some predictions or explain how real-world populations behave, interact. Now, we do this usually on the standard view by generating theoretical hypotheses in the form of comparative claims. So model world comparisons. We compare features of the model system with features of the target system. So this is based on the relation of similarity that we assume, that we presuppose. And then, of course, we need to check whether that comparison is satisfied, whether the target system really shares some features with the model system or whether it doesn't. Okay? So that's the standard view. Now, the problem that I want to address that I think is still present in all accounts, I don't think that any accounts of modeling has even addressed this problem, but because most philosophers haven't even addressed this problem, there is no available solution yet. And the problem is the following: the theoretical hypotheses typically are candidates for truth. They are hypotheses, so they are propositions that we can assess for truth. How? Maybe through observation, maybe through testing. There are different techniques to do that. We don't need to be bothered by that, but the idea is that they are candidates for truth. However, model systems, remember, they are the objects that are supposed to share properties with the target system. But how can they have any such properties? How can imaginary populations really have the property of interacting with each other? How can an imaginary predator population really feed on a prey population? Now, of course, scientists talk in this way, and they use these properties, they attribute these properties to these imaginary populations, but the notion of truth, genuine truth, is not what is at work in this context. We need something else. So we need to clarify also how model world comparisons, which involve reference to imaginary populations having supposedly features that they cannot really have, how can they share these features with real-world target populations? Okay, so this is a problem of truth conditions for model world comparisons. And you have it if you assume that model systems don't exist, or if you assume that they are abstract objects, because abstract objects cannot feed on anything. They cannot die. They cannot increase or decrease their population size. So you have the same problem there, okay? And this is something that has not been recognized currently by those working on this issue. Okay. Now that we know what our adequacy conditions are, and we know what kind of problems they raise for all accounts, and in particular for the fiction view of models, let's have a look at how we can better understand models as fiction before we engage in a critical assessment of what we already have, and then develop a different solution that can address those problems. So just 2 slides on this. 1, make-believe is at the center of the latest developments of the fiction view of models. So most philosophers developing this idea over the past 10 years, even less than that, 8, it is really a very recent development, have deployed Walton's notion of make-believe as a notion that can be used to explain the nature of models themselves, what models are. So Walton's theory proposed make-believe, of course, not in its ordinary notion, but in a sort of philosophically, theoretically developed type of notion. He uses that to understand representational works of art in general, and then, of course, fictions. That's what we are really interested in today. So we just talk about make-believe and fictions. He thinks that works of fiction are analogous to children's games of make-believe. And the idea of make-believe, the notion, is one that fits well with the scientific practice, because make-believe is not something that happens only in our heads, like a solitary, subjective, idiosyncratic type of imagining. It is a social activity. It is something that people can engage in when they share certain rules, norms, conventions within a practice, something that they can participate in. So the modeling practice is a social practice. Make-believe is a social activity involving imagination, and it is one that has a normative character because it involves norms and rules, and it also has objective content. This was one of the main worries that those objecting to the fictional view of models had. If you explain models in terms of the cognitive aspects of the practice, remember, the face value practice is a cognitive claim about scientific practice, one about the way in which modelers think, and if you appeal to imagination, there's nothing more subjective than imagination, right? So make-believe gives an answer to that objection by making it clear that this is a practice, it's a social practice, it has normative constraints, and it has objective content. Objective content is something that can be shared, that we can all grasp. It is not some subjective, non-transparent type of content. Okay, so this is why this notion was so successful in the current development of the fictional view of models. And here is more or less how it works, briefly. This is just a scheme, one that tracks Walton's key element of his notion of make-believe, one that he doesn't himself present this scheme, but this is a kind of analysis of his notion of make-believe that can be used to understand models. So if you think about the Lotka-Volterra model as a game of make-believe, we have first the use of props. Props are central to Walton's account because props are ordinary objects, dolls, toy trucks, but also, of course, the text of a story, the canvas covered in paint, right, for pictorial representation, for example. They are ordinary objects that we can perceive, that exist, that can affect our senses, that can be shared. And they have this special feature that they prescribe imaginings in virtue of certain rules or social conventions, let's say, rules that are understood as being enforced in that particular game, or use the word practice if you want, it wouldn't change much. In this case, the props for the Lotka-Volterra model would be the mathematical equations that I presented to you at the beginning, and of course, the linguistic sentences that were given by the idealizing assumptions of the model. Maybe the graph was also prop, so anything that is a concrete object that has prescribed a certain type of interpretation in terms of imaginings is going to be a prop in this Waltonian sense. Now, what imaginings are the ones that are prescribed by the props? They are what Walton calls fictional truth, and we can distinguish primary fictional truth. Fictional truths have very little to do with genuine truth. Again, fictional truth is a technical notion. We shouldn't try to understand it in terms of genuine truth. They are distinct. Fictional truth is a property of the propositions that are among the prescriptions to imagine of the game. They are the ones that are, what's the word, sorry, that are not elicited, but the ones that are given by the rules of the game, okay? The ones that are allowed by the rules of the game. Authorized, you can also say, that's the word that's used for games of make-believe. Perfect. Okay, now we have the primary F truth in the model, they are the premises. So they are the idealizing assumptions, those sentences that I gave you at the beginning, and of course the mathematical equations. From there, you can get further truth, further fictional truth, sometimes called implied truth or secondary truth, and they are obtained through inferences, which involve some other rules that may not come from within the game. They may come from outside of the game, right? Mathematical rules, in this case, mathematical principles, are the ones that enable the sort of inferences that give you the model outcomes, like predator and prey population interact in a cyclical way. That's something extra that the equations and the idealizing assumptions don't give you at the start. You need to develop the model to obtain that further claim, that outcome. That's the Lotka-Volterra game, okay? Objective content, the propositional content, normative character given by the props with their own rules, and then the principles of generation. And then that is what represents the target system, the model itself. I'm anticipating some things here, but I will come back to this in 3 or 4 slides. To do that, let's try to understand what current accounts have said within this framework. So all of the accounts that I will mention are using Walton's notion of make-believe. So they share the key notions of props, prescriptions to imagine. Also, you see it here, the idea that the objects specified by the relevant prescriptions to imagine would be fictional in some sense, so they would be akin to fictional characters. This is the first development of the Waltonian account into a theory of models as fiction. And this is Roman Frigg's original paper on models as fiction from 2010, where he understands the modeling practice as this indirect representation of reality. Indirect, why? Because we have model descriptions, what I call DM in this graph. They are the props. I already told you, the Lotka-Volterra model equations, the linguistic assumptions, and they, according to Frigg, they prescribe imaginings about a model system that is a type of imaginary system akin to a fictional character. That the model system is the symbol, the representation that stands in a representation or denotation relation with the target. So now we have for the first time, a specification of the vehicle of representation as the model system. Now, Frigg assumes anti-realism about fictional characters and fictional entities, and therefore about model systems as well. So now we have our problems. Aboutness condition, remember, it is a relation between the symbol, the vehicle of denotation, and the denoted represented objects. You need 2 objects for that relation to be in place, but if you are anti-realist about model systems and you say that they are non-existent entities, that they don't exist, sorry, just to avoid confusion, there is nothing there. That's why I have the cloud. You basically miss the symbol that you needed. So philosophers of language have usually focused on the problem of failure of denotation. You have the name or the definite description, and you miss the object that the definite description or the name is supposed to denote or refer to. Roman Frigg is basically giving us the reverse problem. You have the object, there is a target system, but there is no denoting symbol on these accounts, okay? It's strange, I agree. But clearly, if you're trying to give a theory of models as representation and you don't have the representation because you don't have the representational vehicle, then you have a big problem here. Okay, so that's the first problem. Second problem concerning the epistemology of models, how they enable knowledge of reality. Remember model word comparisons? Supposedly, the model systems have to have some properties that they can share with the target systems for the comparison to be one that is true. But of course, you have non-existent objects in this case. They cannot have any properties. So the truth conditions will not be will not be the ones that you want to have real knowledge. Knowledge requires truth. Okay? Now, alternative possibilities. So Amy Thomason has written a paper that will be published soon, hopefully in this forthcoming volume on the scientific imagination. And she develops a view of models as abstract objects. It's just her view of fiction and fictional characters, but translated into this problem. And in this case, the model system is still the vehicle of representation, but we have a model system because it is an abstract object. So at least that problem apparently is solved, the aboutness condition. You have two objects there, and there can be a genuine relation of denotation. Now, my personal worry that hasn't been addressed in the paper, and that would be interesting to address, is how can any abstract object be a denoting symbol? But I will not go into that now. It's a question that I leave open without providing any answer. I think it's problematic. I don't think that it is impossible to answer, but it's definitely something that hasn't been addressed at the moment. Now, the second problem is that concerning the epistemology of models, abstract objects cannot have the sort of properties that they would need to have to share them with ordinary objects. And so, again, we don't have genuine truth conditions in this case. At most, we have fictional truth conditions. So we still need a different account to explain how we can gain genuine knowledge. Knowledge that is empirical knowledge. Scientists are looking for that, not just any other kind of knowledge, okay? So in this case, it would be problematic. Now, finally, the alternative to the indirect view is the direct fiction view of models. And the direct fiction view was a type of reaction to the sort of problems that I already mentioned about the indirect view, in particular, at least one, the one about the missing representational vehicle. So Adam Toon and Arnon Levi developed this view as an alternative that does without model systems. What they claim is that we have model descriptions, they are the props, and now the representation relation collapses onto the notion of a prescription to imagine. So model descriptions represent real-world systems directly, and they prescribe imaginings about real-world systems. I find this idea very problematic because of the following reason. Model descriptions don't involve any reference to any concrete objects, definitely not about any concrete particulars. So if you look at the Lotka-Volterra model, the model doesn't say, imagine of these particular predator and prey populations that they interact in this way. It is about generic or generalized versions of real populations, perhaps. Perhaps you may say that. But it is definitely, the model description is not about any real objects, not in itself. Now, the second problem is that the account that they give of how we learn with models relies on this idea that model descriptions refer to real-world objects. So this idea inherits the same problem. And the idea for the epistemology of models is that we look at the model description and we divide it in parts that are true and parts that are not true, and we take for good only the ones that are true. So the idea, Yablo's idea of partial truth is what they are using in this account of how we learn about reality from models. But because of my first concern, I find this also problematic. Okay. So finally, I don't know how am I doing with time. I think that I've talked a lot already, but oh, that's too much. I will wrap things up more quickly. But so this is the last part of the talk. Now I want to present to you briefly just an outline of the alternative. And the story goes as follows. Okay. So my way of understanding the analogy with fiction, given the problems that we have seen with the previous versions, is the following. So I do share the idea that the Waltonian account is the best one to understand the nature of models, what they are. But I also think that that account can give us something to better understand also the adequacy conditions for models as representations. When we think about the Waltonian account, now I realize you don't see it very well with these colors, but here is how the story would go, I'll tell you. So we have props which prescribe imagining certain fictional truths. That's the key idea. So I retain that, and I claim the following. A model description is constituted by, it has constituents that are the model description, the props, and its content, the fictional truth that the model description specifies, but also the implied truth that we get through the principles of generation. So the content is composed both by the primary fictional truth and the implied fictional truth. This content is, of course, objective because it is propositional content that can be shared intersubjectively, and it doesn't depend upon our own subjective interpretation of the model. It depends upon the rules in force in the model in this particular game. So we have a model description that prescribes imagining a certain propositional content, and D and C, description and content, are the constitutive components of the model. This makes models look very much like fictional stories, where you also have descriptions. In a story, you will probably have certain sentences, strings of syntactic items combined in certain ways. They have their own rules, the syntactic rules, just like the mathematical equations have their own rules, but they are also interpreted according to particular conventions. It's not up to us how to interpret the contents of a particular story. It is up to us to understand what is authorized, let's say, and everything else is a kind of extra that can contribute a different type of understanding of the story itself, but it is not anything objective or that we can claim is definitely part of the story. So in this case, too, we have that distinction. Okay, the content is only the one that is objectively defined by the model description and the principles of generation. Okay, now the identification problem. This relates to the relation between the model and the target. And in this case, how is this solved? Because I am reconceptualizing the idea of a model in a way that is coherent with the model in practice. It's not that I am introducing a new understanding that is not already available in the practice. Remember, we have to explain the practice, not to change it, right? So there is a use of the word model in the model in practice itself, in the way in which scientists talk, that corresponds to this use. So a model is this complex object, and it is, I think, this complex object that can only stand in a genuine denotation relation with a target. Genuine because it is a real relation. Modelers sometimes also talk as if the model system, which now you only have up there, you don't see it because of the colors, I'm sorry. It's sort of ectoplasm coming out of the content that is not part of the model itself, but it's a product of our own cognitive engagement with it, as the model system, right? There are some problems with that. We can talk about that later if you want. I'm not going to say much about it. But let me say at least the following. If they talk as if it was a model system that was representing the real world targets, that cannot be genuine representation. At most, we can interpret that as a sort of pretend representation, pretend denotation. There are ways to explain that notion too, but we shouldn't confuse it with genuine denotation. So this is a way of regimenting the way in which they speak, not a way of changing it, but of better understanding it, of better making sense of it, okay? Okay. Now, the problem of truth conditions. Remember, on the standard view, we have model word comparisons that are theoretical hypotheses that we generate to convert what we have learned about the model onto knowledge of reality. Now, here we have an example. The model predator-prey dynamic interaction is similar to foxes and rabbits dynamic interaction. In this claim, you have apparent reference to the imaginary populations of the model having certain properties attributed to them, and then real-world populations really having the property of dynamically interacting with each other. So Walton gives us the tools to explain these type of claims through his notion of an unofficial, he says. I think that, yeah, unofficial game of make-believe. I was going to say unauthorized, but it's very clear that it doesn't mean unauthorized. It's unofficial because the criteria of correctness for assessing the claim involve ad hoc rules. So in this case, what we have is the following. We have the first part of the claim, which is the attribution of that particular property of dynamically interacting with each other. That is licensed, that's the word that I was looking for before, licensed by the game itself, by the descriptions, the model description, and the principles of generation of the game, right? So that was the model outcome. That is one part. The second part is given to us by reality. If rabbits and foxes interact in this cyclical way dynamically, then it is reality that gives us the correctness conditions for that part. But to assess the entire claim, because we are attributing a similarity to the two, we need to play this larger game of make-believe where we can make sense of the correctness conditions of the first part of the claim in terms of these prescriptions to imagine. So the truth conditions will still be fictional, not genuine. We don't have genuine truth. The comparison is still only fictionally true. Reality gives us something, but the hypothesis itself cannot really be assessed for genuine truth because part of it is not accessible for genuine truth. You see what I mean? Yeah? Okay, so scientists definitely don't want things like fictional truth and these half-truths that don't give us any genuine empirical knowledge. They want genuine truth. So one way to get that is to appeal to something else that they also say, so a second type of theoretical hypothesis that consists in the direct attribution of properties of the model to reality. In this case, we give up a reference to the model, and we just take that property, the dynamical interaction is cyclical, and we attribute it to foxes and rabbits and the way in which they interact. Okay? So in this case, we have really stepped out of make-believe. We are not playing any game anymore. We are attributing a genuine property to a real-world system. And this is a hypothesis that can be tested. You just have to look through time at the way in which they interact, collect your data, and check that the prediction was one that is actually a correct one. Okay? So this type of knowledge, if it is knowledge, will be empirical. It will not be the different type of knowledge that I'm not telling you what type it is. That's the aim of my next project. But for now, let's be happy with these two different types of hypotheses and two different types of knowledge where only this one is genuine, is the one that we want. Okay, at some point, reality needs to play a central role in this explanation. Right, so to conclude, because I think that some of you may have this suspicion. If you haven't, you should have. And here is what should worry you, and something that worried me too. It is about the identity conditions of the model. This is a type of worry that has been already presented in different contexts, in different debates. First, in the philosophy of language, I think Alonso Charge was the first one to have this particular worry concerning Carnap's view of theories. And in the debates on the identity conditions of theory in the philosophy of science, it is one that has been already presented and also answered. So I will appeal to the strategy that has been developed in that context to reply to it here too. And the worry is the following on the new fiction view. The model description is a constitutive component of the model. So this seems to lead to the absurd consequence that every small change in the description will lead to a change in the model, will lead to the generation of a new model. So that you just change one word and you will already have constructed a new model. You translate, right? The way we've done today, talking in English, what Volterra said about his model in Italian, and we have already a different model. That's the idea, okay? However, I don't think that this is a worry that we should really have, because there is a way to address it, and this way depends upon the distinction between the constitutive components of the model and its identity criteria. So I distinguish between what we need to recognize as ontologically fundamental for identifying the object, but I distinguish that from the identity criteria. Any change in the model description will lead to a change in the formulation of the model description, not in the model itself. So the same model can be described in different ways. I just told you, Volterra presented his results in Italian. His model was written in Italian. And we can translate that into English and still have the same model. What we have done is we have changed the formulation of the model from Italian to English. We haven't changed the model itself. So what is doing the work for the identity criteria here, the identity conditions? I'm not going to develop an account here. We don't have the time. And also, I think this is something that would need to be addressed in a different type of paper. But I think that we have different options that have been already proposed by others. One of them, the last one, sameness of truth conditions, has already been deployed by Martin Thompson-Jones in his account of the identity conditions of models. He may be right. Truth conditions, I'm not sure that that's exactly the right kind of notion because of what I said about my account of modeling. Is a translatability that's fine. It's a very famous idea that could be used in this context. Definitional equivalence, maybe. So we have different options here, but it is important that we distinguish between constitutive components and identity criteria. So for that reason, we shouldn't worry about my account in terms of descriptions and content. Okay, and I think I will conclude here. Upshot, very quickly, what we did. We introduced the problem, how do models represent in a way that enables knowledge of reality. We identified two main adequacy conditions that any model needs to satisfy to be a scientific representation. From that, we individuated some problems that any account of models should address. We presented the analogy with fictionalist make-believe as a possible solution, and we critically assessed the standard accounts, and we presented the new fiction view of models as one that can address those problems in this new way, the way I just explained to you. Okay, that's it. I'll stop here. Thank you very much.